Thank you for the introduction. I'm very honored to make the presentation here. I'm Qiancheng, come from Unity Research Center. Now I'm a PhD student in Armin Seyfried's group. And today I will introduce generalized collision-free velocity model for pedestrian dynamics. First, let's watch two videos together. These two videos both show 100 pedestrians evacuated from a bottleneck, and the left video is simulated with a velocity-based model, and the right video is simulated with force-based model. And we can say that these two videos both recognize pedestrians evacuated orderly from the bottleneck, but there's no denying that there are some unusual behavior of agents we can observe in the simulation, not according with the real evacuation process. For example, if you pay attention to the simulation, we can find backward movement often appears in the simulation, and in the real evacuation process, pedestrians are unlikely to move to the opposite direction towards the exit, and secondly, pedestrians turn their body too frequently. And I think it's not according with the reality. So in order to solve these problems, we want to propose a new model focused on merging flow and collision avoidance. Moreover, this model can eliminate some unusual behaviors we mentioned before. Since the model we proposed is based on collision-free velocity model, so I want to introduce this model first in order to better explain my idea. This model is composed of two parts, one speeder part and one direction part. In order to describe this model clearly, I will give an example here. Please look at the right figure. Three pedestrians are represented by three circles with same size, and the pedestrian's eye is represented by a black circle, pedestrian J is blue circle, pedestrian K is red circle. Now I will introduce how to calculate pedestrian's eyes moving direction and speeder according to the position of pedestrian J and pedestrian K. First, the desired moving direction of pedestrian's eye is represented by the black vector in this figure, which is a unit vector decided by the environment. For example, the position and direction of the door. And the influence from pedestrian's J is represented by the blue vector in this figure. And the influence from pedestrian's K to pedestrian's I is represented by the red vector in this figure. And the direction of the blue vector and the red vector is from the centers of pedestrian J and pedestrian's K towards the center of pedestrian's I. And the scale of this vector is decided by a repulsion function. And this repulsion function is an exponential function of the spacing between two pedestrians. And in this figure, the spacing between pedestrian's I and pedestrian's J is the length of the blue segment in this figure, and the spacing between pedestrian's I and pedestrian's K is the length of the red segment in this figure. And when the spacing between two pedestrians is bigger, the repulsion function is smaller and the influence is smaller too. Then we can get the summary of these three vectors, and we can get the moving direction of pedestrians. It's represented by the red vector in this figure. After getting the moving direction of pedestrian's eye, a gray area is formed in front of pedestrian's eye, and the direction of this area is the moving direction of pedestrian's eye, and the length, width of this area is the diameter of the circle. And all the neighbors of pedestrian's eye contact with these gray areas will influence the speed of pedestrian's eye. So in this case, pedestrian's J and pedestrian's K both influence pedestrian's eye speed. But compared with pedestrian's K, pedestrian's J is much closer to pedestrian's eye. So the spacing between pedestrian's eye and J will decide the speed of pedestrian's eye, which is the length of the blue segment in this figure. And we call this distance the minimal spacing in front of pedestrian's eye in the moving direction. And the speed of pedestrian's eye is a linear function of this minimal spacing. When this spacing is bigger, the speed of pedestrian's eye is bigger, and until the speed reaches the desired speed of pedestrians. I think after introduce this example, you can have a clear understanding of collision-free velocity model. So then I will introduce the extension that I made to this model. In the original model, a circle with constant radius is used to represent the edges in the simulation. But we know that the area of pedestrians occupied is changed with the changing of speed. So I use the dynamical ellipse in this video to describe the projection of pedestrians in two-dimensional plane. And in this video, the red vector is the moving direction of these pedestrians. And we can find with the changing of the speed, the shape of these pedestrians is changing too. The dynamical ellipse is already being used in force-based model and has been proved that can have a better performance in some scenarios. So I want to introduce this model in this dynamical ellipse into the velocity-based model and to see what will happen, compare the simulation result. But we both know that the calculation between ellipses will be more complex compared with the calculation between circles. So during this process, we have made some approximations that may influence the results. After making the extension, firstly, we calibrate these models with different shape with the experimental data from the bottleneck scenarios. This video shows the bottleneck scenarios. We change the width of the bottleneck from 1 meter to 2.5 meters. And to get the relation between the flow of the bottleneck and the width of the bottleneck. And the result of validation is given in the right figure. In this figure, the blue circle is the experimental data, and the green square is the simulation result when the shape of edges is circle. And the red triangles is the simulation result when the shape of edges is ellipse. And from this figure, we can say that after validation, the relation we obtained from the simulation when the shape of pedestrians is circle and ellipse both satisfy with the experimental data. And then we use the validated model to do another simulation in our cyclic corridor scenarios. And this video shows a cyclic corridor scenarios, and the length of the corridor is 26 meters, and the width of the corridor is 1.8 meter. Since we want to get the fundamental diagram from this from the simulation in this corridor, so the pedestrians involved in this simulation is from 15 to 175. Then we can get the relation between the density and velocity of pedestrians in these scenarios. In this figure, the green square is the simulation result of circle, and the red triangle is the simulation result of ellipse, and the blue circle is the experimental data. And from this figure, we can find when the density is small, the simulation results of circle and ellipse both satisfy with the experimental data, but in the mid-density, they both not accord with the experimental data. And in the high density, although it's not very obvious, we can find that the ellipse is more accord with the experimental data than the circle. And then I will show two videos to compare the simulation result of circle and ellipse more directly. And you can find the left one is the simulation result of circle, and the right one is the simulation result when the shape is ellipse. We can find after transfer from circle to dynamical ellipse, pedestrians turn their body more frequently. And we can say that dynamical ellipse aggravate the unusual behavior that not easy to be observed when the shape of ellipse is circle, when the shape of pedestrians is circle. So we propose a new direction model to solve these problems. And first, we propose a new way to calculate the moving direction of pedestrians in order to eliminate backward movement. You must remember I have introduced before. In the original model, a pedestrian's moving direction is decided by his desired moving direction and the influence from neighbors. So it can be described by the left figure. In this figure, the dashed vector is the desired moving direction of this pedestrian's eye, and the red vector is influence from pedestrian's j, and the blue vector is the influence from pedestrian's k. And in this case, we can find the summary of these three vectors is the green vector, and towards the opposite direction of the desired moving direction of these pedestrians. So that means pedestrian's eye will move to the opposite direction. So I think this is the reason of the backward movement. So now in the new direction model, the influence of neighbors on pedestrians' eye is always perpendicular to the desired moving direction of pedestrians, and it will towards the left side of desired moving direction when the neighbors is located in the right side of desired moving direction, and towards the right side when it's located in the left side. And there is a special case when the pedestrians is located in front of desired moving direction. And in this case, I think the direction of influence is decided by many factors, for example, like culture, nation, or land. And in our model, in order to simplify, in this case, the direction of influence is always towards the left side. And it can be described by the right figure. In this figure, pedestrian's K is located in left side of the desired moving direction, so his influence is towards the right side. And the pedestrian J's influence is the red vector, and the summary of these three vectors is the green vector and is in the same direction with the desired moving direction. So that means no matter how big the influence from the neighbors, these pedestrians will not move backward. During this process, a dynamical vision area is being used to reduce the probability of blocking. Please look at this figure. In this video, the blue vector is the moving direction of pedestrian's eye, and the blue line is perpendicular to blue vector. The red vector is the desired moving direction of pedestrian's eye, and the blue line is perpendicular to the blue vector. And we can find the blue line and the red line form a light blue areas. We call this areas area I, and that means pedestrians in area I don't influence the moving direction of pedestrian's eye. And that means the white area in this video is a dynamical vision area of pedestrian's eye. And this area is based on both moving direction and the desired moving direction of pedestrian's eye. And compared with constant vision area, dynamical vision area is more flexible and can serve some block caused by the pedestrians cannot be observed when use constant vision area. And last, we introduce a new parameters tau in this model to reduce the turning scale of pedestrians. In the original model, after calculating the moving direction, pedestrian will turn to this direction directly. So now we introduce a time parameter here to make pedestrians turn to this direction smoothly. And these two videos shows our improvement. The right one is the simulation result with the original direction model, and the right one is the simulation result with the new direction model. And we can find that the unusual behavior I mentioned before all disappear in the simulation result of the new model. There are no backward movement, and they turn in their direction very smooth. In order to compare it directly, I use two indexes here. The first index is backward moving index, which is used to describe the backward movement proportion in the simulation. And in this figure, we compare the simulation result of circle and the ellipse with the original model and the ellipse with our new direction model. And we can find that in our new model, we almost eliminate all backward movement. And another index is checking index, which is used to describe the average turning average turning scale of pedestrians in the simulation. And from this figure, we can say that dynamical ellipse will increase the turning scale of pedestrians compared with use circle. And our new direction model can decrease the turning scales. So from the research we mentioned before, we can get two conclusions. The first one is the difference between the performance of circle and ellipse is not very obvious in monosity model. I think the reason may be the approximation we used in the distance calculation between ellipse, or maybe the comparison between the performance of circle and ellipse is not unfair. We don't know the reason, but I think we will do more deepening comparison between circle and ellipse in the future. And secondly, the new direction model we proposed can eliminate unusual behavior of agents in the simulation. But there are still some problems need to be solved in the future. For example, please look at this video. We can find clogging occurs in front of the bottleneck. This is because the width of the bottleneck is too small. I think it's, in this simulation, it's about 0.8 meter. So we will focus on solve these problems in the future. Thank you very much.